there. This video is going to go into some of the basics of solving projectile motion problems. So things that you can always start with when you're solving a projectile motion problem, whether it's a horizontally launched or it's an angled launch. So as we said in the previous video, projectile motion really is just anything that's being influenced only by gravity. It's only interacting with the earth. So the only thing acting on this ball right now is gravity. So we could drop straight down, we could throw straight up, but really with projectile motion, we're talking about two dimensions. So, angled launch, horizontal launch, So, let's start by figuring out if we're only being influenced by gravity. The only thing acting on an object is gravity. What does that mean about acceleration? So gravity is the only thing working on the object. That means its acceleration is straight down at 9.8 meters per second squared. But again, projectile motion, we're dealing with two directions. We have to think about the acceleration horizontally and the acceleration vertically. Well, gravity, vertical, we call that vertical. So with projectile motion, if you're using our standard coordinate system, you always know that the acceleration in the y direction is the acceleration due to gravity, 9.8 downwards. What is the acceleration horizontally? Well, if there's nothing acting on it except gravity, then is there anything pushing it, causing it to speed up or slow down left or right? Nope. We're ignoring air resistance. We do that in intro physics a lot. We ignore, very important things. So if we're ignoring air resistance, there's nothing causing it to speed up or slow down left, right. That means this is zero. And if you combine these two, nothing horizontal, lots in the vertical, we get straight downward at 9.8. So anytime you're dealing with projectile motion, these two things are true. So we can always, in our chart of variables, we can always put these two in. So let's focus on a horizontal launch because that's the easier one. So for something that's horizontally launched, so we know its initial velocity is purely horizontal. What else is going to be true? Besides these two, what else is going to be true? Let's look at our chart of variables. Now we have two directions, two dimensions that we're dealing with, so our chart of variables has to include both of those. So here is my horizontal information, and here is my vertical. All right, V initial, A, T, Y, Y, Y. Okay, so what's true about a horizontal launch? What can we always fill in this table for an object that's horizontally launched? I want you to think about it, and how many of these do we know, no matter what the problem is? So long as it's horizontally launched, what do we always know is true? So take a minute, think about it, and see what you can come up with. Think about each of these 12, and write down in these 12 which ones you know will always be this certain number. So take a minute, hit pause, go for it. If you need a hint, then I'll give you a hint that there are three things for horizontally launched objects. There are three things that are always going to be the same. Well, two of them are right here. So AX is always 0, AY, negative 9.8. Hello, cat. So I gave you those two already. Those are always true for projectile motion. What else is going to be true specifically for a horizontal launch? Well, the initial velocity is horizontal, which means that my initial velocity is all in the x direction. So this right here is the initial velocity, but that's going to change. Well, can we make an assumption, well, make a rational logical conclusion actually, about this right here? If all of the initial velocity is horizontal, is this thing moving up or down to start with? Nope. This right here is always true. So for horizontally launched objects, these three pieces of your chart will always be the same because we always know there is no horizontal acceleration. All the acceleration is vertical due to gravity, and since it's horizontally launched, there's nothing, it's not moving up or down to start with. So I hope you got those right. Let's move on to the angled launch then. So, what would be true for an angled launch? I don't know why I'm drawing this on a table. So now, VI. We have something that's being launched up at an angle. So I'm going to erase. And I want you to do the same thing. What do you think you can always fill in for these, out of these 12 variables, for an angled launch projectile? And I have a helper. Oh, Jeeves, he's my helper today. You want to look at the camera? You look at the camera? Yeah. Okay, down you go. All right. Does that give you time to think about it? So, for an angled launch projectile, well, we always know that. Again, these two are always true no matter what for projectile motion. So we've got those two. We know our acceleration. Now, do we know VIY or VIX? Well, we know VI. And what's true about angled launches is you are always going to have to break up the initial velocity into its horizontal component and its vertical component. And so this right here and this right here, neither of those is this number. You can't just say if this is 12 meters per second, this isn't 12 and this isn't 12. We have to do something in order to get these, because 12 is this side of the triangle. And we need this side and this side. So the things that are always going to be true for angled launch, this is always going to be VI cosine theta, and VIY is always going to be VI sine theta. So long as you always have theta compared to horizontal, this will always be true. So there are actually 4 things that will always stay the same. I mean, these numbers will change, but you always know these 4 will be these values right there. We might have different initial heights, initial final positions. This, well, we know these 2 are the same because there's no acceleration. Don't know that, and we know that the time is the same, but we don't know what that time is, just like the rest of it. Now, one thing about angled launches that I want to make sure you think about is direction. So typically when we're talking about projectile motion, a lot of times we're talking about sports and, you know, various types of balls. So if we've got a football or a baseball or a volleyball or whatever, you know, it's going up and up, and those are starting upwards. But let's say I'm in my basement and I see a centipede over there. I'm going to fire this rubber band. I'm going to fire this at a downward angle. All right, okay, apparently I shouldn't have trimmed my fingernails. Boom. Okay, we won't try it. So what if we fire something initially at a downward angle? What then? What changes? So I'm going to say that rubber band was going off at an initial velocity downward. What does this change? What do we have to take into account? Well, this is a direction thing. We're still going to have to break up the initial velocity triangle into its initial horizontal and its initial vertical. That's exactly the same. It's still the cosine component adjacent, it's still the sine component opposite. But what we see here is with our standard coordinate system, the horizontal component would be positive and this would be negative. We would have a negative initial velocity in the y direction because it's going down to start. Likewise, if we have an initial velocity going like this, if we're popping a volleyball up and to the left, we would have a negative VIX and a positive VIY. And so you've got to be careful to think about the signs, because this isn't something that the math will tell you if you're just using this angle. So if you're just drawing your triangle like this and just taking into account this angle right here, you have to tell the problem, the math, you have to tell the math that this is a positive, this is negative, or this is positive, this is negative. So that's something to be careful with, especially if something's being fired left or down into the left even. You want to come say hi too? Here, we'll have a second cat. Two cat video. This is Worcester. He is the partner to Jeeves, of course. So, what do we have here? Oh, now I've got cat fur. All right. On to thinking about the equations. So we've been talking about how we need to have two charts of variables, right? So our charts of variables, we have to deal with the horizontal and the vertical separately because they are independent of each other. AT, so y, 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 x, x, x. All right. So once you get your charts filled out, typically we're like, okay, what do we want to solve for? And then you find an equation that has that variable in it. So let's think about our equations. This is one of the equations we've been working with. All right, so x final, x initial, v initial t, 1/2 at squared. But again, independence of the two directions, up, down, and left, right, have nothing to do with each other. So when we're doing this math, we also have to keep it consistent in only one direction. So that means that you have to have this equation with VIX and AX. So there'd be the matching equation, y final equals y initial plus VIYT, oh, I'm running out of space, plus 1/2 a yt squared. So we've got these matched paired equations, one all in the x direction, one all in the y direction. You can't mix and match because this has nothing to do with that. They're independent. Remember, there's a line here. So the only thing that connects these two is that time is the same. So, you know, if I could solve this equation for time, I could put that time over here because the time is the same. But I can't put VIY in here and have x final and y initial and AX. You have to keep everything in one direction. So instead of 3 equations now, we actually have 6 available to us. 3 in the x direction, 3 in the y direction. So v final equals v initial plus AT. So v final x, v initial x, AX, v final y, v initial y, AYT. And then the third one, v final x squared, this is getting complex, v initial x squared plus 2, acceleration in the x direction times change in x. And then the last one, v final y squared, v initial y squared plus 2ay change in y. So there's our 6 equations now. So remember, you have to keep these two separate. You can't mix and match at all, and now we have to keep the equations all in their single direction, which means we've got 3 times 2. We can do all these equations in the x direction, all these equations in the y direction. You have 6 available equations to solve the problems. Typically, you're going to have to use at least 2 to solve a problem. And usually with projectile motion problems, usually you're going to use one direction to solve for time, and then once you have time, you can pop that into the other direction to solve for whatever you need for. So you'll be doing a lot of solve for time in one direction, use the other direction, because time is the only thing that connects those two. So that's some basics of how to do problem solving with projectile motion. And after this, you're ready for a whole bunch of sample videos, just examples of how to solve different projectile problems. And I'll try for the beginning, for practice and for videos, I'll try to make sure to label whether it's a horizontally launched object or an angled launched object. On a quiz, we actually have 2 objectives for projectile motion. One is being able to solve the easier horizontal launch, that's a C level. And then we have the A level, which is harder, solving an angled launch. All right, I think that's all I've got for you. I hope this made sense. I hope it was helpful, and good job for watching.